Thank you so much. It's a great pleasure to be here at this wonderful venue with this incredibly enthusiastic and committed audience. I really appreciate the invitation. So a little about me. I want to give you a capsule summary of the talk. I wake up every day and have the really good fortune to be able to say that I can go to work and build a new instrument to look at the universe in a completely new way and make an observation that no one has ever made before. That has been getting me going for the last 30 years of my career, and I hope I continue to do it until they drag me off. And today I'm going to talk about one of the instruments that we're trying to build at Keck to answer very fundamental questions about the universe that haven't been answered before. So I'll give you the background of where those questions come from, and they relate to, as Taft mentioned, the intergalactic medium, which turns out to be most of the normal matter in the universe. And we don't have maps of this intergalactic medium, even though it connects the entire universe. It runs between galaxies, and it's the basic backbone, the architecture of the universe. So we're trying to actually, for the first time, make those images and maps with this new instrument, the Keck Cosmic Web Imager. And what we would see with these kinds of maps is an image like that on the sky, a beautiful image of how the universe is structured. So before I get to that, I want to make sure that my talk is clear. So I want to define a few terms which make it a little bit easier. We talk about normal matter, distinguish it from dark matter, and we usually call it, as astronomers, baryons, to make it a little bit shorter than normal matter, but it's basically normal atoms. We talk about this medium between galaxies, the intergalactic medium, and sometimes we refer to the medium that is closer to galaxies but still in the intergalactic medium as the circumgalactic medium. And one of the most important spectral features, it's an atomic transition of the fundamental two levels in hydrogen. We call it Lyman alpha, and I'll be talking a lot about Lyman alpha. That's what we're trying to detect. Yes?
Can I give you this mic? You're a little muffled. I know that. Be willing?
Absolutely. Can you hear me better? Yeah, it sounds very strange to me, too. Sorry about that. Okay. So the first experiment that I worked on was a sounding rocket, and actually thought of this experiment. It was not the primary experiment. It was I was given 80 seconds to do an observation, and I conceived of an experiment to measure fluctuations in the ultraviolet glow that would actually constrain galaxy evolution over the last 5 billion years. I had 80 seconds to do that, and it actually worked, and we did constrain galaxy evolution. I was quite fortunate. I actually did 2 thesis projects as a student. My second one was a shuttle experiment on a getaway special, which is a tiny canister that flies basically without any information until you get it back. You don't know whether it works. You don't know if you got data or anything. They tried to launch it 5 times, and they finally launched it the 5th time, and they were getting so amused and whimsical about the process of launching a space shuttle that the astronauts actually dressed up for the group photo in that funny picture. It turns out that we got the data back, and I had a software engineer who built some of the programming to look at the data, and I called him up and said, have you looked at the data? And he said, yes. How's it look? He said, well, there's nothing there. And I said, no, that's not possible. Look again. And he called me an hour later. This is now about 11 p.m. at night. He said, oh, I had a bug in the program. And actually, it worked beautifully. And so I actually, that night, analyzed the data, and I got this spectrum. And there's this line in the spectrum, an ultraviolet line called carbon-4. It's what we were looking for with this experiment. It was amazing to me. And it's the first time in my life I had the experience of seeing something and knowing something about the universe that no one else in the world knew about. And what that told us was that we live in a dynamic
Milky Way something called a galactic fountain, in which exploding supernovae eject gas into the halo of the galaxy, and that gas cools and rains back on the galaxy and produces this fountain of gas flow. And by doing that, it produces this carbon-4 emission, which we detected. So that was fundamentally new component of the Milky Way, which we discovered. More recently, in 2003, and this is something, again, I wanted to do as a graduate student, survey the sky in the ultraviolet band. We launched the GALEX satellite, Galaxy Evolution Explorer, a NASA small explorer. It's still up there. It's still observing. And it's obtained many beautiful images. This is Andromeda in the ultraviolet. And it has made many discoveries, one of which was the discovery that the star Mira, which has been known for 400 years to be an unusual variable star, had a 2-degree long tail due to its stellar wind interacting with the interstellar medium. And that made the Washington Post. So that's been a very exciting and fruitful project, and I'll be talking a little bit about some of the science and how it relates to the intergalactic medium. It also has the benefit of fitting on a Rose Parade float. And I was very proud of that. We were above the Mars mission. Okay. So I first want to give you the reason why we're trying to image the cosmic web. And one of the major enterprises in astrophysics is what I like to call cosmogony, understanding how matter went from the tiny fluctuations that were created by the Big Bang to, hopefully we don't fly away, to the Earth and all the steps in between. Yes, sorry. So this is the timeline for this amazing evolution of the universe, starting from the Big Bang and a catastrophic inflation of the universe, of enormous, many orders of magnitude increase in size. Following that, the matter recombined to form from nuclear matter to normal matter, and finally began to collapse into gravitational clumps that ultimately form galaxies and clusters of galaxies. And that's happened over about 13.6 billion years. And it's an amazing fact that the universe has managed to take this incredibly tenuous intergalactic medium in which there's one atom per cubic meter, convert that into galaxies in which there's 1 million atoms per cubic meter. And this process is what I'll be focusing most tonight. But beyond that, star formation, planet formation, star formation and planet formation has created even denser systems, the suns and planets that we know. And the total range of density is 30 orders of magnitude from the intergalactic medium to the sun and planets. So I like to think of this universe as a machine that generates out of this tenuous gas stars, planets, and even people. Maybe some of your friends are on that. So how did this happen? So the initial seeds of structure formation in the universe have been mapped by the cosmic microwave background satellite WMAP and balloons before that. And these are tiny fluctuations in space-time, very parts per million in the density, in the local density of matter. And we now have computer simulations, gigantic computer simulations, that predict how these tiny fluctuations will evolve over time and turn into the galaxies and structures we see today. So there are the seeds, a piece of that, the universe, at the time the cosmic microwave background was formed. These form lumps of dark matter, and the dark matter dominates the matter in the universe, except for dark energy, which I'll mention in a minute. And these lumps of dark matter basically tell the rest of the universe, the normal matter, what to do. They pull the normal matter in. And we understand dark matter by simply using Newton's laws. But then the baryons fall into the dark matter lumps, and they go along for the ride initially, but then lots of complicated physics goes on when the baryons start colliding with each other. So baryons interact with themselves. It's hard to do this, but you know, you can clap your hands. That's baryons interacting with baryons. Dark matter passes through itself, so there's no interaction. So the baryonic physics is very different, and so we give it a name, which is gastrophysics, which apparently is also a name for creating very interesting cuisine using the laws of physics, I hope. Maybe not the laws of good taste, but... Okay, so how does structure form? Well, there's this sea of noise, of fluctuations, and it can have a different spectrum. It could be really bassy, it could be really trebly, or it could be something in between. And if it's really bassy, it's called pink noise, and you tend to get structures like pancakes. That's loud. If it's in between, you get two-dimensional collapse into long filaments like a web. And if it's blue noise, emphasizing the high-frequency side, you get collapse into lumpy structures that look like meatballs. And it turns out, and this is very technical, I know, but it turns out that it's the one in the middle is the closest. And we get structure which looks like a cosmic web. And that cosmic web intertwines all the galaxies in the universe and all the clusters of galaxies. And when the web, the filaments of the web intersect, you get clusters and larger density regions. And there are galaxies strung out along this web like beads of dew in the early morning. Okay, that's the first question. The second question, where are the baryons? Well, you may be familiar with the fact that if you look at the total amount of mass energy in the universe, 70% is dark energy, and I'm sure Brian Schmidt talked about that. 26% is dark matter. We don't know what it is, but it has normal gravitational interaction. It just is something we don't know what it is. And then there's this 4%, unfortunately, of baryons. That's all we are. And in fact, if you look at the baryons and do a pie chart of that, only 1% is in stars and galaxies, and the other 3% is in the IGM. We look at the galaxies. It's very hard for us to look at the IGM, even though that dominates the normal matter in the universe. So we can ask two questions about where the baryons are. First of all, we can ask what is their temperature and density. And if you look at this diagram, this is all the plasmas in the universe, from the densest plasmas in the sun to a fusion tokamak, lightning, a neon sign, etc., a nebula. And then the least dense, the most tenuous, is the IGM. And the other dimension is temperature. And the IGM is actually quite warm, 10,000 to a million, even 100 million degrees, or 10 million degrees. And so we don't actually know what temperature the IGM is and how much is it various temperatures. Now, these are all plasmas, and according to my son's chemistry teacher, a plasma is not a form of matter. But, yeah. So some of that matter collapses and heats up and becomes that million-degree, what we call the warm-hot intergalactic medium. Here it is collapsing, and it's basically the process which is in your engine, which condenses the air and heats it up to the point where it's ripe to be flash exploded. And simulations show this happening. Basically, the color tells you the temperature. Blue is 10,000, and orange is more like 1,000,000. And so in the densest regions, it's collapsing and forming this very warm intergalactic medium plasma. And it's more difficult to observe when it's warm. Now, the second question about where the baryons are is, where are they in space? And this is a simulation that shows where the dark matter is and then where the galaxies are with respect to the dark matter. It's going to show just the galaxies, and then it's going to come back and show the dark matter. We believe that the IGM is basically following the dark matter because the baryons are told what to do by the dark matter. The dark matter says collapse, the baryons collapse. What they do after they collapse is more complicated. Now, this will go into a cluster, and then it'll show again the dark matter, and we believe the IgM, surrounding that cluster if the screen doesn't blow down. There's the dark matter reappearing. So you can see that the dark matter and the IgM fills in the space between the galaxies. But that's based on a simulation. Okay, the third question of cosmogony is how do galaxies get their wonderful diverse properties? This is just a selection of different kinds of galaxies. Some of them are forming new stars, and some of them are elliptical galaxies that are not forming stars anymore. And you can argue about, just like children, whether they get their properties from nature or nurture. Galaxies, we can argue about that. The nature might be, well, they fall into a dark matter halo, we call it, the lump that it falls into. And that may just tell what the galaxy, how to be over its life. But it may live in an environment that changes the galaxy over time. So it may be nurture. And the location in the cosmic web may determine this. The classical way of classifying galaxies was the Hubble tuning fork. Elliptical galaxies basically have stopped forming stars and they've become red in color. And spiral galaxies and irregular galaxies are forming stars actively and are blue in color for that reason, or ultraviolet bright. What we've discovered with GALEX is that there's a population of galaxies which seem to be transitioning between these two types, ellipticals and spiral galaxies, and there's something in between. They're transitional. They may be going this way, they may be going that way. We don't know. In fact, we're probably looking at galaxies that are doing both. It's interesting to try to understand this, to classify galaxies in a relatively simple way, just like we classify stars on the Hertzsprung-Russell diagram. Temperature tells us basically the mass of the star. Cooler stars are lower mass, hotter stars are higher mass, and the brightness is correlated with temperature on the main sequence when they're burning hydrogen in their cores. We can fairly well predict the evolution of stars on and off this main sequence over their lifetime. We can make an analogous diagram for galaxies where now the vertical axis is the degree to which they're forming stars. You can think of it as being gas-rich because there's new gas to form new stars, and these tend to be spiral galaxies. The gas-poor stars are not forming stars very much. These tend to be the elliptical galaxies. So the gas content is fundamental to the nature of these galaxies. And we can actually imagine how a galaxy might evolve on this diagram. This is filled in, by the way, with GALEX images of various galaxies on this axis. Here's a pretend galaxy. It's getting more mass. It's forming stars. But it's starting to lose the gas, so it's becoming red. Then it gets some new gas, and it forms more stars. So it seems to be going all over the diagram. In fact, if we make a model of a bunch of galaxies and follow their evolution over time on this same diagram, we see they start out forming stars, so they're gas-rich. Then many of them lose the gas, and they stop forming stars. And then later on, you can see some of them are moving back up and forming stars again. So they're getting new gas. So what they're actually doing is changing their personality from elliptical galaxies to spiral galaxies, and some do it many times over cosmic time. It's an amazing new fact about galaxies that we've understood. So then the question is, how do galaxies get their gas? Because gas is clearly driving this evolution. So the classical picture was that galaxies, there's a cloud of gas, it slowly collapsed, and stars formed from that gas, and that was pretty much it. It was very boring. But the modern picture is much more complicated. There's streams of gas, there are mergers, lumps coming in. It's quite complicated, but clearly stuff is coming from the outside, the IgM, and driving the evolution of the galaxy. We also know much from work at Keck over the last 2 decades that the star formation in the past in galaxies was very different. So star formation in the past was very rapid, and the galaxies back then looked very unusual. They're very lumpy. They kind of disky, but kind of irregular. And we think we understand why that is, and I'll tell you that in a minute. Whereas now, galaxies have a much more regular look. They're forming stars at a much lower rate, and they've been doing it, the galaxies we're looking at seem to have been forming stars at this rate over many billions of years of cosmic time. So we can distinguish two ways in which galaxies get their gas, which might distinguish between these two modalities of galaxy evolution. So the first one is you basically have the baryons fall into the dark matter halo, and as they collapse, they heat up, just because the same reason anything falls, it heats up. But then that slowly cools over time, and that cooling gas rains down on the galaxy and continues to fuel ongoing star formation, just like a gentle rain, which we're hoping not to get from the sky, condensing out of the water vapor. But we need to understand how this very rapid star formation burst in the early universe occurred. And there's a new model in which there's streams of gas flowing directly from the intergalactic medium, fueling this very rapid star formation, a fire hose of gas in which the galaxies are trying to consume as fast as possible. And that's why they look so different, and that's why their star formation is so rapid. We actually have evidence, even in the universe today, that galaxies are getting new bursts of gas. And this is an elliptical galaxy in a visible picture, and a GALEX picture showing the ultraviolet, showing star formation occurring in a ring outside the galaxy where new gas has probably been accreted recently. So now, how do galaxies lose their gas, and why do we think they lose their gas? This is a simulation, like the ones I showed you before, of what the Milky Way should look like. But this is the dark matter. So the Milky Way should be surrounded by, the sky should be full of galaxies, small dwarf galaxies. But we know it's not. There are handfuls of dwarf galaxies. In fact, the map looks like that. And we think we understand that these dwarf galaxies are very bad at forming stars. And the reason probably is that they blow the gas out immediately because they're so small and they don't have enough mass to hold the gas, and they lose that gas before it can form a real galaxy. And we have evidence that that's happening in the early universe. There are winds of gas expanding out of galaxies. The entire galaxy is exploding due to this rapid star formation occurring in these early universe galaxies. And we can measure that by measuring this shell of gas in absorption. The atoms basically produce an absorption line in the spectrum, and the location of that absorption line tells us the gas is moving toward us in a shell that's an exploding galaxy. We also see in local galaxies that here's a galaxy in the optical, which is moving through the intercluster medium of Virgo. And it was forming stars, but the gas is being stripped out because the galaxy is moving through an ambient intercluster medium, which is stripping out the gas. And it's basically shutting off star formation in this galaxy. This was an image obtained by GALEX, again. So that's another way of galaxies losing their gas. So here's the picture we have. Here's a galaxy. It's very complicated. It's sitting in a dark halo. It's sitting in a filament of the intergalactic medium. That filament is collapsing and getting hotter. In that filament are cold streams, even more dense filaments of colder intergalactic gas flowing in towards the galaxy. The galaxy has winds coming out of gas. Gas can actually come out in a fountain, like I talked about, my shuttle experiment. And there can be gas in the dark halo orbiting around, waiting around to form stars in the future. So a reservoir of gas. So it's a very complicated but fascinating picture of how the galaxy connects to the intergalactic medium. It's a two-way street. Matter is going in, matter is coming out. So we would really like to get a picture of this. So how do we do that? This is what the cosmic web would look like if you take one slice and then move through the slices through space. You see this beautiful picture. We'd like to get that picture. Well, one of the techniques we use is atomic absorption. So hydrogen has a fundamental transition of Lyman alpha. Photons, which are red, transmit. Blue ones transmit, but the right wavelength gets absorbed, excites the atom, and then it gets scattered in a different direction. So you see an absorption line at the wavelength you want to see. Now that's at 1216 angstroms if it's close to us, but cosmic expansion, of course, redshifts the light, so we can actually relate the wavelength of the light to the distance from us, because more distant things are redshifted more. And so we measure a spectrum of the cosmic web, and we look at absorption due to Lyman alpha at various cosmic distances, and they appear at various wavelengths in the spectrum, and we can make a one-to-one correspondence between the wavelength and the location in space. That gives us effectively a one-dimensional map using this absorption transition. And the problem with a one-dimensional map is it's a one-dimensional map. It doesn't help very much. It tells you that there's stuff here, there's not stuff here, but it doesn't tell you that you're living on a planet with oceans that are 70% of the surface area and so on. Very interesting Earth we live on. This doesn't tell you what it is. Does anyone guess? It's my favorite city. And this, it's not mine, but it's someone's brain. Donated to science? No, I think it's still alive. So there's clearly more information in a two-dimensional image or a three-dimensional map than in a one-dimensional skewer. So what we need is emission. And there are two ways to get emission. The gas in the intergalactic medium is ionized by quasars, and that recombines to form emission that produces this line at 1216 angstroms. Or the gas can be heated by either gravitational infall or super wind outflow, as I've showed you. That excites the electron, and then it de-excites and produces a photon, which we detect, again, in emission. And again, using redshift, we can correlate that with distance and construct real maps, or real pictures. So I'm doing that with a project I call the IGM project over the entire history of the cosmos. We have to do it in the ultraviolet for the nearby universe, and to do that, we have to go into space. So we're designing a satellite to do that, called ISTOS. We actually have funded to do a balloon called Fireball to do that at redshifts of 1, where things are relatively close and the universe is relatively mature. But in order to look at the universe in the epoch of star formation, which I showed you before, we have to look at redshifted Lyman alpha that falls in the optical band all the way from 3,500 angstroms out to 10,000 angstroms. And for that, we need an optical instrument designed specifically to do this job, and that's CWI, the Keck Cosmic Wave Imager. This is the team working on Keck Cosmic Wave Imager, and it's a great team of people from Caltech, from LIC, from Keck Observatory, and this is actually the address of our astrophysics building at Caltech, 1216. So that is our goal, that is our quest, from the ultraviolet all the way to the epoch of reionization. How do we do it? Well, maybe some of you are familiar with what would be called a nebular or long slit spectrometer. This is a comet, and in order to take a spectrum of this, we put a slit down, and we get a one-dimensional image, and then we put that through a spectrometer, and we get, in the other dimension, a spectrum. So it's a two-dimensional detector, spectrum in this direction, image in that direction. So we can do that with a slice of the cosmic web, which is one-dimensional. We can get effectively a two-dimensional image by taking a spectrum of that. And because redshift gives us distance along the line of sight, we get this two-dimensional picture. But what we really want is a three-dimensional picture, because the cosmic web is three-dimensional. Looks like that. So we want to say x, y, and redshift, or wavelength, in the third axis. So how do we get that? we have to use a new kind of spectrometer that uses something called an image slicer. Basically, it's a bunch of reflective slices that are tilted at different angles. And one part of the slicer sees one part of the image and reflects to one part of the spectrometer. And the other part of the slicer, and this one has actually 24 pieces, redirects this piece of the image to a different part of the spectrometer. And there are a total of 24 of these slices, and we then reconstruct that as an image. And I'll show you how that works. So imagine we have 3 slices of the cosmic web at 3 different distances. Here is one at 11,354 million light years from here. Lyman alpha folds at a wavelength of 4864 angstroms. 11,362 million light years. The wavelength is 4876 angstroms. And a little bit farther, 4888 angstroms. So 3 different slices at equidistance. Okay, what do we do with that? We illuminate the image slicer with the light from the telescope. And we get these, we divide it up into these individual slices. And each slice falls on one of these reflective facets, which is tilted at a different angle. So there are the 3 slices being put on the 3 facets. And now here are the images falling in the facets. And the slicer basically redirects the light in the following way. It turns it from a square image into a long slit. So we can put it through a long slit spectrometer. And this will be the 3 different wavelengths. And none of the information will be confused, and it's all sorted out. And then in order to reconstruct the cosmic cube, we take the spectrum, we put the slices back together, then we arrange them in a cube, which can be done in software. And we make this what we call a data cube. So this is the position, this is the other position, and then the 3rd dimension is wavelength, which stands in for distance. So we get a 3-dimensional image of whatever we're looking at, and in this case it's the cosmic web that we started with. However, there are some challenges to looking at the cosmic web. It's not dark matter, it's dim matter. And nature, of course, tries to hide the signal. It likes to make our jobs challenging because that's what it makes us stronger and smarter. How does it hide the signal? It hides it behind detector noise, city lights, air glow, zodiacal light, and so on and so forth. And I like to think that the Holy Grail is behind all those things, waiting to be imaged. Here is a color code showing you how different regions of the IGM in a certain unit, which I've normalized to be 1. So the average IGM is about 1, and it can range from 100 in the brightest regions around galaxies to, in the filaments connecting galaxies, 0.1 and even 0.01. So what are these other things in these units? City lights. Well, fortunately, not so bad here. In fact, the sky is very dark here. But in Temecula, near Palomar, that's actually a picture of Temecula. That's what we see, the spectrum of sodium. We get a lot of sodium in our spectrum at Palomar. And it can be 100 to 1,000 times the brightness of the IGM. Air glow. The Earth's atmosphere is alive with atomic and molecular transitions, and they have structure. They have waves that go through the sky. These are waves of OH emission. There are also some lightning sprites you see. So the sky is alive, it's spectrally complicated, and it's time and spatially variable. And so we have a trick for dealing with that, which I don't have time to talk about, but it's a completely, it's called knot and shuffle. It's a little dance we do with the telescope and the detector, and it seems to work pretty well. It allows us to measure 2 regions of the sky, and even though the background is varying, or the foreground is varying very rapidly, we can subtract it accurately. Less variable in time, but something that's quite bright, is the zodiacal light, the dust cloud that surrounds the solar, that is the residual material from making the solar system and from the collision of asteroids, produces this band of light in the sky, which is in the ecliptic plane, and it has the spectrum of the sun. It doesn't vary too much on the sky, but we have to subtract that out. The galaxy, all the stars in the galaxy reflect off the dust in the galaxy, and the dust is variable in different areas of the sky. There's cirrus, there are clouds, and so on, like this. And that produces a diffuse background that we have to subtract off in order to not confuse it with the intergalactic medium. Then there are all the stars and galaxies, which of course we spent the last 50 years or 100 years studying in the sky. We're not interested in those. We want them to go away. Because we're interested in the stuff between the galaxies and way beyond the stars. And so we have to be able to image the galaxies and stars very accurately and then remove them from the data in order to produce pictures like this. So even though it's really hard, we want to do it because there's so much physical information. This is a simulation showing the density, how it increases with cosmic time, the temperature, the metallicity. Basically, galaxies are forming stars. The stars are forming heavy elements. Those heavy elements are being launched into the intergalactic medium, perhaps seeding new galaxies with new metals. And that metallicity is growing around the galaxies. And the gas is flowing in all the time, and some of it's flowing out. So the velocity field has an enormous amount of information about this process. So this very complicated gastrophysics is determining the evolution and formation of galaxies. And this is the kind of picture we really want to get. And this is the kind of picture we can potentially get by mapping emission from the cosmic web. So we're building CWI to do that. It's based on a prototype called the Cosmic Web Imager at Palomar. And that CWI is getting excellent data and proving to us that we really can do this experiment. And CWI will be a beautiful new addition to the Keck suite of instruments. It's much more flexible than CWI. It's built to service the general community of astronomers and to do all sorts of imaging spectroscopy of complicated and extended objects in the galaxy all the way to the edge of the universe, reionization of the universe. It has a wide spectral range, very flexible modes that allow us to do all sorts of different kinds of observations. It'll take advantage of very excellent imaging in the dark sky on Mauna Kea, and we're planning for first light of half of this in 2014. And because of that, there's a whole slew of science applications, things that we can't do currently at Keck we'll be able to do that will really complement all the science we've been doing to date at Keck. Here's a picture. I'm not going to explain it. It's a big instrument. This is about 3 meters tall. It's heavy. It sits at the Naismith focus. And if you have any questions, I can answer later about how it works. It will work. But some of the things it might be able to do. This is one we thought of. In fact, a prospective student at Caltech said, I want to do exoplanets. Can you do exoplanets with your new instrument? And I said, I hadn't thought about that. And then I said, well, we have this thing called nod and shuffle. Okay. And it turns out you can use that and look at a reference star and then look at a star with an exoplanet that's transiting in front of the star. And what you want to measure is a very subtle change in the spectrum due to the transit. It's the absorption of the atmosphere in the exoplanet. And the only way to do that is to have a very good reference measurement. And it turns out we can do that with our instruments. So that's something new we hadn't thought about we'll be able to do. We discovered this object with GALEX. It's called the Blue Ring Nebula. We don't know what it is, although we're honing in on it. We have Keck data now. There is this nebula. It radiates only in the ultraviolet. There's an explosion which maybe happened about 2,000 years ago. Something happened to the star. It's an otherwise fairly normal star. And there was an explosion. So that's all I know, or that's all I can tell you right now. But we have some suspicions. And we could use CWI, or KCWI, to measure the spectrum, because this basically doesn't radiate at all in the optical. But we think that if we added up all the light in the entire field of view, we would actually get a measurement and constrain the properties of this mysterious object. I mentioned Myra, again, another galaxy discovery. This is the optical picture. I just have to show this because it's beautiful. It radiates, again, mostly in the ultraviolet. and it's very, very, very faint. But we'd really like to be able to map this emission and understand the kinematics of this turbulent wake, which is being driven off the star by its shooting through the interstellar medium. And it's a fascinating system and may tell us a lot about stellar evolution after stars leave the main sequence. This is a really interesting thing. An explosion goes off in the galaxy. And it's too late for us to see the explosion. It already passed the Earth. But it reflects off a cloud, and that light wave hits us later. We can look at a cloud and actually see the spectrum of a relic explosion and tell what kind of explosion it was. It's called a light echo, and I'm very looking forward to using CWI to finding these. Star clusters, globular clusters, you may be familiar. There's a controversial issue about whether they have black holes in the center. This is, of course, not a real photograph. We know of only one definitive black hole at the center of the galaxy, of course, discovered by Keck. There may be less massive black holes in the center of globular clusters. And the way to figure that out is to get excellent imaging spectroscopy with very high velocity resolution and map the kinematics of the stars. Basically very similar to the kind of work that's being done by Andrea Ghez in the center of the galaxy, but using the integrated light from this cluster with KCWI. We can do that. We can map nearby galaxies and map the flows of gas in the galaxies. I haven't talked much about that, but the gas flows in galaxies form stars and form star formation regions. And the star formation in galaxies actually back reacts against that gas and may regulate that star formation. Here is star formation occurring in M51, the Whirlpool galaxy. And where you see star formation, if you look at this picture, this is a measurement of the turbulence of the gas measured by CWI at Palomar. And the gas is much more turbulent above regions of star formation than it is in regions of less star formation. So that's suggesting that the star formation is actually stirring up the gas, which is possibly regulating the fundamental laws of star formation in galaxies. This is a beautiful image of what we believe to have been a dwarf galaxy which fell into this large galaxy and produced this stream of debris. This is stellar debris, and all of the information we have is imaging. We would like to be able to take a spectrum and tell us how fast that the stars are moving and what their spectral or content is in terms of how old the stars are. And that would tell us more about that relic collision between a dwarf galaxy and the galaxy itself. We can do that with KCWI by basically taking the image slicer and just adding up all the light and making an uber spectrum of everything in that box to try to constrain the physics of this very important event. So this just illustrates that CWI actually can make images of this group of galaxies called Stephan's Quintet. This is a ground-based image, the Deep Sky Survey, the Digital Sky Survey, and this is a CWI image of the same. This is basically a spectral image, and we've added up all the wavelengths to produce an image itself. And you can look at the individual slices of wavelength and let them fly by. So now we're flying through wavelength. And what you see is various line emission from the galaxies. The galaxies are rotating disks, and because they're rotating, some of the gas is blue shifted and some is red shifted. So you'll see the gas pass from one side of the galaxy to the other as you see that rotation going from slice to slice. And I won't play the whole thing, but there it goes again. So that seems to work. Now, quasars are basically galaxies that have this black hole in the center that are enormously bright for a very brief time. And they light up the gas around them, the gas which may have enormous information about the processes which form that galaxy. So we call that the circum-QSO medium. And we have observed a quasar, which was observed by Keck, by Chuck Steidel. This is a narrowband image of the Lyman alpha near the distance or redshift of the quasar. It shows lots of gas clouds. And we have CWI images showing these gas clouds may have filamentary structures. This is another slice, a third slice. There seem to be large-scale structures around the quasar that we're getting with CWI, and we'll get much other data with KCWI on this. Finally, what about the cosmic web? We really want to detect that. Here's a simulation, 300 million light years on a side, of emission in Lyman alpha at 1 redshift. This is a blow-up of that, and this is how we would make an image by mosaicing the KCWI field of view on this simulation. And I want to tell you about one observation we've done, which I'm very excited about with CWI, which shows the potential of KCWI. It's one of the most exciting results I've had in my career. And I want to explain it to you just very briefly. First of all, when Lyman alpha is produced by the cosmic web in emission, it actually produces a funny profile. At low density, you get a single line, but at high density, you get a double line. And I can explain that to you in questions later. But that double line profile is predicted and very characteristic of cosmic web emission of higher density gas. This is a known Lyman alpha emitting object that was discovered by Chuck Steidel at Caltech and imaged and spectra were taken at Keck. We observed the region around it with CWI at Palomar. And this is a map of 2 lines surrounding the line which is at the redshift of the object. So this is a map of the emission which bathes that double-peaked profile. And what you see is it's noisy, but there appears to be, centered on the blob in the center, filaments extending out, in fact, going into the central object. And there are 2 galaxies at the right redshift that are connected by one of these filaments. That's a very large structure, 1 million light years in size. Now, I've been looking at this now for a year, and I'm trying to understand what's going on with the system. And remember that we generate data cubes in wavelength and 2 dimensions of position. We can look at this cube either by slice, as this shows, or we can cut this cube in a different way and look at it in versus position versus wavelength, and that gives us a different view. And I did this for the first time only a month ago, and it was the second time in my life where I've gotten a result, first time anyone has ever seen this, that excited me so much that I couldn't sleep. This is a prediction of what one of these spectral images would look like. This is a prediction of emission from the cosmic web. And this is the double line profile that I showed you for Lyman alpha if the gas is static and not changing. And this is if the gas is actually flowing and moving due to gravitational interactions and the actual motion of the gas flowing into these dark matter halos. So this is one of these where gas is clearly flowing into this lump of matter there from the cosmic web, and it looks like this thing. And this is what we think. We think it's due to, it's getting wider because the density is increasing, and it's blue shifted, but the gas is flowing towards us. So what happens if we take this one piece right here and cut it, make a spectral image in the orthogonal direction? This is what we get. It looks like that. There's gas up here, which is low density. It's got the double peak. As it moves towards the central object, it gets broader. And that means the gas is getting more density, more dense, and it's getting more turbulent, clearly. There's more going on as the gas is flowing in. This is actually a story telling us that gas is flowing into a protogalaxy and fueling the new star formation in this forming galaxy. And it looks exactly like the simulation. It's amazing. And I looked at that and I said, I cannot believe it's that good. But that's what it is. It's one of the most exciting things I've ever found, and it proves that KCWI is going to be an unbelievably powerful instrument that will open up a whole new field of observations in the future. So I thank you for listening to me. It's been a delight to talk to you, and I look forward to the day when KCWI will make the dark sky come alive.